Hi, my name is Cedric. Welcome to my presentation. I'm going to talk to you about Ease.ml Snoopy, the system we built in order to perform an automatic feasibility analysis for machine learning application development. As a group which understands a little bit about machine learning, potential new users tend to ask us whether given their data, they can do machine learning at all. The straightforward answer to that is that it really depends on the target accuracy you want to achieve. A machine learning consultant typically would take the data from the users, look online for a similar data set, the best accuracy achieved, and the method which achieves this best accuracy on this similar data set, in order to give a rough estimate of what is possible on the user's data set. A more automatic approach would be to take the user's data set, go to your favorite AutoML system in order to get a state-of-the-art model. The problem with that approach is that it doesn't give an upper bound of what is possible at all. Furthermore, this approach is very time-consuming, costly, and last but not least, might be harmful for the environment. In Ease.ml Snoopy, we want to combine the best of both worlds. We want to follow an automatic approach without requiring to train a lot of different models. Therefore, users provide the dataset and the desired target accuracy, feeds this to Ease.ml Snoopy, which snoops at the data, hence the name Snoopy, in order to give back a decisive answer whether the target accuracy is reachable or not, because the data needs to be cleaned or enriched. The good thing is that this is possible, but far from trivial. Notice that this problem is a 50-year-old, well-known non-trivial problem. In machine learning terminology, what we want to do is to give an estimation of the base error. Informally, the base error of a classification problem is the minimum achievable error rate. What I mean by that is the error rate that any best classifier might achieve. One straightforward question would be, why is a zero base error often not achievable? In order to illustrate this, let me give you some examples coming from ImageNet, the well-known state-of-the-art dataset for computer vision problems. The next two pictures are coming from the test set of ImageNet and are either labeled as a rooster or a hen. The first problem, why zero base error is often not achievable, is when there are multiple objects on the same image. For instance, this image is labeled as a hen but contains both a hen and a rooster. The second source of non-zero base error lies in label noise. This image, for instance, is labeled as a rooster but is neither a rooster or a hen. We make use of controlling the label noise in order to verify the accuracy and the quality of our estimator, but for more details, we'll refer you to our demo paper. As I said before, there's a long history in estimating the base error. In our work, we focus on the paper given by Kolar and Hart in 1967 on nearest neighbor pattern classification. Kolar and Hart provided a theorem which says that for sufficiently large training set size, the error of a nearest neighbor classifier is less than twice the base error rate. The direct implication of this is that we can obtain a lower bound estimation of the base error by taking the nearest neighbor classification error and dividing this value by 2. The problem with that approach is the term sufficiently large. In order to illustrate this, let me plot the convergence rate of KNN run on CFAR10 raw features. We see that the lower bound is far away from the state-of-the-art given last year, in December last year. Why are we so far away? Well, as often in machine learning, what we have here is the curse of dimensionality. The number of training samples needed in order to reach a good estimate of the base error is very high. How can we tackle this problem? In our approach, what we make use is the power of pre-trained data transformations, publicly available via TensorFlow Hub or PyTorch Hub. What we do is we take the dataset, run inference through a pool of pre-trained data transformation or embeddings, run KNN on every single embedding, and take the minimum achievable error rate in order to get an estimation of the base error. Again, on our CFAR10 example, if we plot the lower bound estimation on a set of pre-trained transformation, we see that taking efficient NetB7 features results in a reduction of 8.3x compared to the raw features. Now let me demo our system to you. We build our demo as a simple web UI, and we run a REST API in the background. The UI is very simple. First, we choose the type of the dataset and then select the dataset itself. The only thing we need to specify is the desired target accuracy of 80%. Next, we're able to select different pre-trained embeddings. We'll start with the raw features simply. When starting the evaluation, we see that our web service starts running KNN first on the test set and then on the training set. The convergence of the training sets is shown here, and as we haven't run all the training samples, the system is still running. Once we run it on all the training samples, we can see whether the lower bound estimate is below the target error or not. As it is above, the desired target accuracy is not achievable. By selecting more embeddings, we'll see more curves on the plot, and if one of the curves is able to go below the desired target accuracy, our system will output achievable. With this, I conclude my talk, and I'm happy to answer questions in the live Q&A session. Thank you very much.